talks provided by our friends from the quantum industry. So our first talk will be Thomas Alexander representing IBM Q, and he'll be telling us about IBM Quantum Experience and Qiskit.
So thank you very much, Nathan and Xanadu, for having me. I actually just came from our hackathon in Japan, and I've attended a couple of these so far. And I think they're like returning to the hackathon portion of the day. I think it's a really great experience to do stuff you normally wouldn't do and meet people you normally wouldn't talk to. So branch out a bit. Today I'm going to be heading a bit deeper down into the stack. Quantum machine learning isn't exactly my area of expertise. I'll try and touch on it a little bit and how we fit into the scheme of things, but I'm also going to talk a bit more about hardware today. So quantum computing at IBM and our roadmap to quantum advantage. So as Seth was saying, the field of quantum computing and quantum science is quite old. But in 2016, we launched the Quantum Experience, putting the first quantum computer in the cloud. And since then, we've really been scaling up and kind of getting ready for what we hope will be a new era in quantum computing, which we're going to refer to as like the quantum advantage era. So of course, Gavin mentioned we've had this Google supremacy work, which I think is a really great work. And there might have been a bit of a disagreement between IBM and Google, but I don't get into any of that. We prefer the term advantage, which we want to actually show usable advantage on over some classical problem. So that's what we're really trying to do. And so how are we trying to do that? Well, in the near term, we're looking at educational material, software such as Qiskit, and building open standards and metrics for the community as a whole so that we have a common language and framework to talk, to speak or to work within. So we're working on building a quantum community, putting quantum devices in the cloud, Qiskit, our open source platform for quantum computing. And then moving forward on the science portion, we're looking at how do we use short depth circuits, thinking about quantum benchmarks in the near term, and then quantum advantage demos. So we understand that we're going to have a noisy quantum computer, so how can we work around that? So we're talking about approximate quantum computer in the NISQ era. So machine learning, chemistry are great candidates for showing quantum advantage. And then moving forward, we're thinking about logical qubits and encodings and how we do that within both the quantum hardware and the classical hardware that encompasses that. Thinking about how do we design better codes, maybe distributed quantum computing, and with the end goal of building a universal fault-tolerant quantum computer, that holy grail. So the IBM Quantum Experience, it's our platform to access IBM's quantum computers in the cloud, both physical quantum systems as well as simulators. So we have some cool numbers, I think, to have really shown how much this has grown. As we have over 140,000 users, 220-ish papers, 2,600 forks on GitHub, and many thousand stars. So it's really been cool to see the quantum community grow and actually use the devices. So we've run over 115 billion circuits on our hardware at this point in time, which is really awesome. It's crazy to see how in use these devices are. We have over 15 systems in the cloud now. So you can access yourself, quantum computing, IBM.com. You can use our quantum experience, where you can gain access to devices, maybe work with the graphical interface, or use notebooks in the cloud if you don't want to set it up on your own computer. So how are we doing qubits at IBM? So right now, I'm not saying it's the way we're going to do it forever. Maybe superconducting qubits are the way forward for now, but there are other very promising technologies as well. We're using fixed frequency qubits. So we really just have these anharmonic oscillators that are a Josephson junction and a capacitor in parallel. And there's pros and cons to fixed frequency qubits. So the pros is they're really stable. So we have better noise properties than most tunable devices, relatively high coherence, and we have all microwave control electronics. So this is both a pro and a con sometimes, but it allows us to have kind of more cost-effective control for both our single and 2 qubit gates. The cons are we often have frequency collisions. So in fabrication, the Josephson junctions they might come out a little bit different than we design them to, and that might cause them to collide in frequency with another qubit, which can cause problems. And this leads to really stringent fabrication properties that are required. So how have we been doing? So here I show a plot of both our C0 error rates, readout error rates, as well as our T1 and T2 times. And you'll see as the years have gone on, our general properties is coherence has gone up, gate errors has gone down. It's pretty good. I'm actually very impressed in the hardware progress we've been able to make with superconducting qubits. I think we showed a T1 time of around 500 microseconds earlier this year for a single qubit device, which I, quite frankly, was kind of blown away that we were able to achieve that. And so we've also been exploring with different topologies and different generations of our internal hardware systems along the way. So how do you access these devices? So our near-term quantum computing framework is Qiskit. It's on GitHub, it's open source. You can join our Slack community if you want to talk with any of the researchers or get some help with it. And it's easy to install with just pip install Qiskit, Python 3 and 2. Oh no, it's only 3, my bad. And so there's really 4 components to Qiskit. There's Terra, which is the foundation. So this allows programming both simulators and quantum systems at the level of quantum circuits and the pulse schedules that lie underneath these circuits that control the classical control hardware. There's Ignis, which is our framework for characterizing error in devices, mitigating noise, and just in general kind of examining these near-term physical devices. And then there's Air. It's a high-performance simulator framework designed to work tightly with Qiskit. And Aqua, which is our applications framework. So this is where you'd find pluggable algorithms for tasks such as optimization, machine learning, and quantum chemistry. So really, Terra is the foundation, and to understand how it all fits together, we need to look at this first. So Terra has a compilation pipeline that takes you from your quantum circuit to one that is optimized for the device, and then even allows you to then further compile that to the underlying pulse level instructions that control the quantum hardware. And it has a variety of quantum information tools and visualization tools built within it. And building a circuit in Terra is quite easy. You just initialize a quantum circuit, append gates to it, and then unitary gates and projective measurements. And then it's designed to be agnostic of hardware, so you can use both simulator backends, our own backends through IBM Q, or backends through another provider, such as maybe Alpine Quantum Technologies has an ion trap quantum computer that interfaces with Qiskit. And within Qiskit, there's a full compiler pipeline that's designed to be configurable, extensible, and open for research. So you're able to build your own series of passes to manipulate your quantum circuit and your pulse schedule. And then there's a lowering procedure that takes you to your pulse instructions. And these operations are done in a way that they're cognizant of the underlying device properties, as these vary quite heavily from device to device in this near-term era. And like I said, it's a device-agnostic compilation framework. So you're able to define a circuit that's just a circuit in the gate model that might use gates that are non-native to your device and maybe that don't follow the connectivity schemes of the system you're targeting. And then these are going to be compiled to the native gate sets of whatever hardware you're looking at, such as like a trapped ion system that might use the Mohr-Sorensen gate, or a superconducting system that maybe uses the CNOT gate. So within Qiskit, there's 2 levels of control. We have the traditional model of control, which is the gate level model of control. So you're programming your quantum program in terms of unitary gates and then projective measurements. And then we have a lower level of control that's really done in a way that's aware of the classical control electronics that are going to manipulate your quantum system. And here you might schedule pulse level instructions, frame changes, tell your digitizers to open up and take actual, physically sample the voltages on lines and discriminate that from a set of samples to a 0 or a 1, as you traditionally think with a measurement. So I think this is a cool video that shows how this process actually works. So in Qiskit, you send a program down through the cloud, and it's going to interface with the quantum control electronics. So this is kind of an antiquated system, but these are going to send out microwave pulses into our quantum computer, and they're going to go down and interact with the qubits, say manipulate them with a gate or do a measurement, and we're going to get back out a classical signal that's going to be amplified in the fridge, and then the classical control electronics are going to take that signal, sample it, and say, is this a 0 or a 1, and then this result comes back to you. So this is underlying kind of what a quantum computer is this classical control that needs to manipulate the systems. So it's really easy in Qiskit to go through this compilation pipeline. So here's a circuit to produce a Bell state. We're going to take this circuit and then transpile it to a circuit that's actually optimized for the underlying target hardware, such as the U2 gate, which is going to implement the Hadamard gate. And then we can take this transpiled circuit and feed it into the scheduler, and it's going to output a series of pulse level instructions that are going to implement this circuit in the classical control hardware. And so this is a hackathon about quantum applications, quantum machine learning. So we do have a framework for quantum applications, and this is Aqua. So it's a pluggable framework where it's designed to interface classical algorithms with quantum components within those algorithms. And it's built into these pluggable pieces that can be, you can slot one component in for any other component. So you can build up kind of arbitrary permutations of algorithms. And it's for applications in things like machine learning, chemistry, finance, and optimization. So here's a brief example that I'm going to skip over to keep things brief. So what's the general flow in a classical quantum hybrid algorithm? So we're going to start with by defining an algorithm in Aqua. It might be a quantum SVM, it might be VQE, and then this is going to output a set of quantum circuits to be run on the device. There might be, say, entangular proportions, parameterized rotations, and then measurements in this circuit. And this is going to go through our compilation pipeline, the transpiler, which is going to run a series of optimization passes to improve your circuit for the underlying device. Then it will go through the scheduler, which will also do likewise at the classical level. And this is going to be sent to a device, whether it be a simulator or the underlying hardware. And then it will come back, and we might use Ignis to do error mitigation on, say, the measurement results. This is going to be fed, these counts are then going to be fed back into the algorithm, and the algorithm is either going to output a classical result, or maybe it will continue processing and run some more quantum components. So this is a machine learning hackathon. So I wanted to kind of talk a bit about some ideas in machine learning that are interesting to me, given that I'm much lower down in the stack. So some areas of machine learning comes into play in quantum computing. So we have components, or we have, people often think about how we might accelerate classical machine learning with a quantum subroutine, such as, say, the linear algebra that Seth was talking about earlier today. And then we have different methods that other people have talked a lot about today that look to explore high-dimensional Hilbert spaces with these ansatz circuits, like the quantum SVM or the Boltzmann machine. And then we can also use machine learning to look at characterizing quantum systems, because we have these near-term devices, and a lot of the time they're often kind of black boxes to a degree. And we can look at designing machine learning algorithms to characterize these systems. And then, of course, we're designing new algorithms in the classical machine learning realm that are inspired from quantum machine learning. And these are also cool ideas. So within Qiskit, we tend to focus on these two, so exploring the high-dimensional Hilbert spaces and characterizing our quantum systems. And we really have two separate components that look at these two different areas. So Aqua is an application, it's the applications framework, so it will implement these SVM and Boltzmann type applications, but then Ignis is the characterization framework, and it's going to maybe do techniques such as Hamiltonian estimation or gate calibration. And I really hope we can look at using kind of some new techniques from the machine learning world to improve the approaches to these problems. So one area where we have much more control now is really this pulse level interface. And I'm hoping we can do some things like that Chris and I used to work in, such as Bayes and parameter estimation and other techniques in this framework. Thanks. So now I'm going to talk about something that I kind of came up on the way over here. How might you use pulse level control to do some unique quantum quantum machine learning. So what can you do with this level of control that you might not have within the gate-based model? And so let's briefly, others have touched on the quantum SVM. And one key component of the quantum SVM is you have to prepare these kernels which use these ONSAT circuits that you then want to learn the parameters in these ONSAT circuits. And in a lot of these approaches, they're going to use some gate that just gives you some amount of parameterized entanglement. And when you decompose this, they often use C0 operations, which may not be native to your hardware. So maybe you want to use an operation that's actually native to your hardware to be more efficient. Because if you just wanted to do this C0, if you just want to insert a little bit of entanglement, you really don't have this option other than, say, trotterizing your circuit, which is, of course, going to be very high def, and it's just not going to work in these near-term devices. So if you have pulse level control, here's the cross-resonance gate that Gavin mentioned earlier. You might actually be able to parameterize this gate in terms of, say, the amplitude of the pulse or the duration of the pulse, and then insert this gate into a quantum circuit. You can promote this pulse up to a quantum circuit within Qiskit and use this within your machine learning algorithm to kind of turn on a little bit of entanglement for a brief period of time. So here's a brief example. I show how to do this in Qiskit. So we create an entangler gate, and what this is this is based on my stupid pulse designer, which assumes that the rotation done by the entangler gate is going to be proportional to the area under the curve in the Gaussian square pulse. So, you know, it's not the real world, but you might insert something like grape if you wanted to do it more intelligently. So we have this state preparation circuit with these Hadamards. Then we apply our entangler gates that are parameterized in terms of this theta. And then when we do our pulse scheduling, we're going to decompose this theta into some underlying cross-resonance pulse. And then we might surround this whole, we might run this on a circuit, on a quantum device, and then wrap this in an optimization, a classical optimization algorithm for these parameters theta. So I haven't done this, but it should work if somebody wanted to try it. If you want to start using Qiskit, we have a bunch of tutorials online, variety of topics from machine learning to more traditional quantum algorithms. We have a website for educators, including a textbook that uses Qiskit. I think it's a really great learning resource. One thing I really want to personally show going forward or do is kind of look at teaching quantum control and some quantum engineering techniques using pulse level control. And finally, we have our IBM Q Awards that are open right now. If you want to come up with an idea during the hackathon to submit to this, there's a bunch of money and a variety of different competitions on the line. See if you can, get dual purpose out of things, maybe. So yeah, thank you very much. If anybody has any questions, feel free to ask. Yeah.
Questions for Thomas?
Yeah. So I was actually a bit hazy on this. The cross-resonant gate is the sort of natural gate for this IBM
Yes.
thing. But can I access that directly
Yeah.
in Qiskit
Uh,
at the gate level?
It's at the gate level. It's not currently exposed, and this is because when you implement the cross-resonance gate in hardware, it's never going to be exactly what you expect from theory. And so the results, if you input some parameter, it's going to be less than expected. Like when we expose a C0 operation, it's
like a perfect C0.
yeah, it's a perfect C0, and it's been done, kind of implemented with a lot of corrections of local unitaries. So there's no reason in practice that we can't do that. In fact, the way we do it currently is with this pulse level control.
So you can't get it at the pulse level?
Yeah. And in fact, that entangler thing I was showing was essentially just doing that.
Right.
The cross-resonance gate is very easy to do. You pulse on your control qubit at the frequency of your target qubit, and that's that for some period of time.
And what I didn't say in my previous talk was there's a smarter way of taking gradients of the cross-resonant.
Okay.
I'd be
I'd be interested in hearing that. You might.
It's optimizable.
Okay, cool. Yeah.
Any additional questions?
Thanks. I just want to ask, for all these different topology architecture, they actually related to like, are they actually universal in the sense that you can always choose two qubits even if they're not directly connected, and you want to apply synology?
Yep.
Is that possible?
It is always possible to insert a series of swap operations for some number of qubits that's less than the total qubits of the device there.
So they're actually, because I guess if it's based on errors in interaction, there's a hard and CNOTs based on the same architecture?
Oh, so we're not implementing a universal all-to-all CNOT operation. We implement universal quantum circuits by we have supported CNOTs between connected gates in the topology, and then we're swap mapping the state of the qubits to enable that all-to-all connectivity at a virtual level.
So the closer the two qubits are, the easier to do CNOT.
Yes.
So does a application engineer actually needs to know this, or is there an algorithm that runs in the background that will take your whatever the application engineer design and optimize it for this architecture?
So the compiler needs to know this, and ideally the compiler is smart enough, and currently this is the way that it's implemented, it's smart enough to know the quality of the gates, the quality of the qubits, and the connectivity of the entire system. And it will attempt to choose the optimal layout that the application designer would choose if they were being smart as well. Of course, in practice, some algorithms are better than others, and some compilation passes are better. You know, some do good, some do bad. Sometimes the application designer is better. The hope is that, like within classical computing, it used to be more efficient for somebody to write assembly by hand if they were smart to understand the underlying devices. But over time, we come up with near optimal algorithms for large sets of, everyday use cases.